We have been discussing about problems related to the first law of thermodynamics for steady state steady flow process, and we will continue with the problem solving in this particular lecture. So, the first problem that we will consider in this lecture is problem 4.6. A heat exchanger as shown in the figure is used to cool an air from 800 Kelvin to 360 Kelvin, both states at 1 megapascal. The coolant is a water flow at 15 degree centigrade 0.1 megapascal. If the water leaves at saturated vapor, find the ratio of the mass flow rates. So, let us draw the schematic in the board and then we will solve the problem. This problem is very similar to the condenser problem that we solved. So, we will not take much time for it. So, as we discussed earlier, the purpose of the heat exchanger is to exchange the heat between the two streams. Here the streams are air and water. So, we will construct a control volume. So, straight away there is no external heat transfer, kinetic energy and potential energy changes are neglected, and m dot 1 is equal to m dot 2, right. This is air state 1, this is state 2. So, m dot 1 is equal to m dot 2 is equal to m dot air, and m dot 3 is equal to m dot 4 is equal to m dot water. So, from this equation you can write m dot air into H1 plus m dot water into H3 is equal to m dot air into H2 plus m dot water into H4. Okay. So, what is asked is what is the ratio of m dot air by m dot water. So, m dot air into H1 minus H2 m dot water into so what is asked is m dot water by m dot air. So, now H1 minus H2. So, these values, see these are air with a widely varying range of temperature. So, it is better to use the air table instead of considering constant CPCV. So, in the appendix of any book of thermodynamics, you will find that in the property tables you also have properties of air, and there it is assumed that air is ideal gas, but CPCV may not be constant. So, then you can get H1 minus H2. So, H1 and H2 both from air table. H3 is water at 15 degree centigrade with 0.1 MPa. This you can approximate as HF at 15 degree centigrade. This is compressed liquid, but its enthalpy can be approximated as saturated liquid, and H4 is Hg at 0.1 MPa. So, if you calculate all these, the ratio will be 0.1766. Okay. We will consider the next problem, problem 4.7. In this problem you see two steady flows of air enter a control volume as shown in the figure. One is 0.025 kg per second at 350 kPa 150 degree centigrade, this is state 1, and the other is 450 kPa 15 degree centigrade state 2, both with low velocity. That means you can neglect the kinetic energy of the inlet states. A single flow of air exits at 100 kPa minus 40 degree centigrade state 3. The control volume rejects 1 kilowatt heat to the surroundings and produces 4 kilowatt of power. Neglect kinetic energy, basically neglect changes in kinetic energy, that should be a better way of stating this. Determine the mass flow rate at state 2. Okay. So, let us work out this problem. Let me, as our standard practice, draw a schematic of this. So, for solving problems I always prefer that we show positive direction of heat transfer and positive direction of work done as we have used for the derivation. If instead of heat addition it is rejection, it will be negative. So, that because if we show the direction itself as opposite, then sometimes there can be an algebraic confusion in writing the energy equation. So, for this control volume let us write mass balance and energy balance. Energy balance, first law let us see what is given one by one. So, it is given that first of all you can neglect changes in kinetic energy and potential energy. So, these changes you can neglect. So, you can write q dot and m dot 3 you can write m dot 1 plus m dot 2. So, q dot is given, q dot is, so let us write the given data here. W dot is 4 kilowatt. So, now you can write q dot so let us see what is given. State, so m dot 1 is, so let me write with a different color. M dot 1 is 0.025 kg per second. M dot 2 is not known, and all the fluids are air essentially. Let us look into the temperature range -40, 15, 150. So, temperature range is there, it is not as large as say 500, 600, 700 like that, but temperature range is there. So, I would ask you to solve the problem in two ways. One is find out these property differences from air table, approach 1, find out these property differences by assuming this as this. So, if you do it in this way and substitute the values of heat and work, you will get m dot 2 is this. So, you can try with looking into the air table without using this approximation and see what mass flow rate you will get. In this problem you will get a value very close to it. Okay. So, we will work out another problem. So, that problem is next problem 4.8. So, a proposal is made to use a geothermal supply of hot water to operate a steam turbine. So, steam turbine requires high enthalpy fluid, right. So, there is a geothermal supply of hot water, it is used to operate a steam turbine. The high pressure water at 1.5 MPa 180 degree centigrade, that is corresponding to state 1 here, it is throttled into a flash evaporator chamber which forms liquid and vapor at a lower pressure of 400 kPa. The liquid is discarded, that is the saturated liquid comes out of the evaporator and the saturated vapor feeds the turbine and exits at 10 kPa with 90% quality. The turbine should produce 1 megawatt. Find the required mass flow rate of hot geothermal water in kg per hour. Okay. So, let us draw the schematic. This is typically the symbol of a throttle valve, this cross. So, let us write the values here. State 1, state 1 is water 1.5 MPa 180 degree centigrade. State 1 prime, what is it? So, we have learned the throttling process. State 1 prime, across the throttle valve you have negligible change in enthalpy. So, H1 prime is equal to H1. So, then this entire process, this is throttled to 400 kilopascal, right. So, water at 1.5 MPa 180 degree centigrade, it will have H1 is equal to 763.5 kilojoule per kg. From table. So, this you can write this is HF at 400 kilopascal, the pressure at which the flash evaporator operates, and this is HFG at 400 kilopascal. So, you know H1, so from here you can find out what is X. So, X you will get 0.07439, this is the quality. See, what is the definition of quality? It is the mass of vapor by total mass, and out of this steam vapor mass is coming out here and liquid mass is coming out here. So, this is nothing but m dot 2 by m dot 1. Okay. So, this is the very important step. So, it is not just a formula, but you have to understand the physical meaning of the definition of quality, mass of vapor by total mass, and here only the vapor is coming out. Then you can consider the control volume as the turbine. Steady state steady flow process. We neglect heat transfer across the turbine, we neglect changes in kinetic energy and potential energy, and m dot 2 and m dot 3 are the same, and the turbine produces 1 megawatt. So, this is 1000 kilowatt. Normally we use kilo units for substituting all the values, because enthalpy values are in kilojoule per kg as you get from the table. So, that is why I have put it in kilowatt. So, from this equation H2 is, you already know what is H2. So, what is H2? This is the state 2 is given, state 2 is 400 kilopascal and quality equal to 100%, and state 3 is 10 kilopascal, quality equal to 90%. So, you can calculate what is H2 is equal to Hg at 400 kilopascal and H3 is equal to Hf plus x3 Hfg at 10 kPa with x is equal to 0.9. So, you can get, and m dot 2 and m dot 3 are the same. So, from this equation by substituting the values you will get what is m dot 2? The answer required is what is m dot 1. So, from this equation m dot 1 is m dot 2 by x. This x, not this x, this is x 3. So, this if you convert it into kg per hour unit, so it will come out as kg per second. So, if you convert it into kg per hour unit, then answer is m dot 1 is equal to 123.075 kg per hour.
It is not point, it is 123.075.
123075, right, 123075. Okay. Okay. So, let us stop here today. We have solved a few problems related to the steady state steady flow energy equation. There are many situations when the process in the control volume is such that the steadiness of the process is not maintained and it is an unsteady process by its intrinsic nature. In the next lecture we will try to see that if it is an unsteady flow problem, then how to do a control volume analysis. Thank you very much.